So today we're going to talk about motion on an inclined plane, which is a fancy physics word for a ramp. When Firefox is installing my updates, and we'll start in a few moments. So when that's done, I'll show you this link here, hopefully, that it's still up and running. So just having a look at this, the screenshot that I have here, you'll see that we've got a box here. What do you think these green arrow thingies are here?
Acting upon the object.
They are forces acting upon the object. Excellent. Now what do you think that they would be? This one right here, which is straight down, would be gravity. And you don't have to jot this down. I'm going to go through it in a second, right? But you're right. That would be gravity, weight force, right? And what do you think this one here would be? Yeah, that is the normal force, exactly. You might remember, like if you've got just a box on a flat surface, you've got weight force down, and you would have normal force up. But then I think you can use your imagination. As I increase the angle, then remember the normal force is always perpendicular to the ramp, to the surface, right? But gravity is always down. So in this type of situation here, what would you say about the weight force and the normal force? Are they equal to each other? Are they balanced? In the just something sitting on the tabletop, Garrett, they wouldn't be. They would balance, right? Yeah. But would they be balanced here now that I've got it on an incline?
No.
They would not be. When you've got an unbalanced force, right? A net force, what does that cause a mass to do? It starts with the letter A. Accelerate. And as you well know, things that are on ramps tend to slide down the ramp, right? Accelerate down the ramp. So what causes that? Well, it's this component of the weight force. It's that down the ramp component of the weight force. And then there's also this component here, right? That sort of pushes it down, kind of thing. So this one here I refer to as FD for down the plane. It's my own little convention. Thank you very much.
I'll use X.
You could use that. I mean, it's because X tends to be left to right, whereas this is it's a special situation, right? So I use FD. Okay. Now this force here, is the object going to be accelerating up like this or down into this thing? No. These forces would have to be what? Those would have to be equal. So while this is technically the normal force, I refer to this as the normal force component of gravity because the numbers are the same, right? Just opposite direction. Does that kind of make sense? I'm going to go through this all again right away. Okay, so I'm just sort of giving you the big picture, and then I'll sort of break it down a little bit. Okay, really, what I was doing was wasting time until this was up and ready. Let's see if it's ready to go. Oh yeah, this is fun. So, okay, so what we've got here is what I want to show you or describe for you is kind of what I was just talking about. Basically, it's the free body diagram of an object that rests on a ramp. Okay, so here's my ramp here. Now this angle down here, this theta here, do you see that it's equal to that angle? Does that make intuitive sense to you, that those angles would be equal, right? Like if it was flat, right? If this thing were flat, this angle would be 0, and then this angle would be 0 too, right? And as I increase that incline, this angle here increases by the same amount, right? Does that make sense, Mike? Think about what it would be if this was 90 degrees, right? If it was like this, right? And I rotated that all the way to like that, right? That would be 90 degrees. Would this then not look like this? Right? Be 90 degrees, right? Oh. Okay, go away. All right, so that's sort of step one, is that those angles are equivalent to each other. Now, as I pointed out before, this is the weight force caused by gravity. It is straight down, right? Gravity is always straight down. But some of that gravity is acting down the plane. Think about it as a component. Think of these as like the X and Y components, right? But it's not really X because it's not horizontal, and it's not really Y because it's not straight down. which is why I came up with the names FD for down the ramp. It's the component of the weight force that acts down the ramp. And you might remember me having in the other diagram a normal force here, which is always perpendicular to the surface. And so I just call this one Fn as well. Technically, I'm incorrect, but it's equivalent to the normal force, right? Like the number is the same. If the normal force here was, say, 10, this value here would be 10, right? So I just use it as sort of a label. It's not 100% accurate. Which one of all those forces is actually causing it to roll down the ramp?
No force down.
The FD, really, right? The bigger the FD, the faster it goes, which would mean that if the angle of this is steeper, little voice crack there, right? If the angle of this is steeper, then FD is going to be bigger, which means it's going to roll down the ramp faster, right? Does that make sense? Now, quite often, this FD right here, quite often people will draw it right there. Is that okay?
Yes.
Okay, so all I've done is just taken that component out and put it right there. If there was friction on this ramp, which way would it be?
Up to
Yeah, it would be up like this, right? This would be friction force if it exists. For now, we will just worry about frictionless ramps. Okay? This weight force, by the way, is equal to mg. Mass times gravity, right? mg. So our job today is to come up with how am I going to find out the value of FD and how am I going to find out the value of Fn? Because they're going to be important. Okay, so when an object sits on an inclined plane, two things happen. Gravity acts to pull it down the plane, and gravity also acts to push it against the plane perpendicular to the plane. Okay? And these are simply, this Fn and Fd are simply components of the weight force. Do I have a picture drawn here somewhere? No, I don't. Okay, so I've got weight force, perpendicular, Fd, right?
You don't have a sheet for this.
No, you don't. I don't know if you want to write that down or not. When an object sits on an inclined plane, gravity acts to pull it down the plane, that's the FD, and gravity also acts to push it against the plane perpendicular to the plane. And the greater that angle, what happens to the values of FD and FM? As I increase the angle, what happens to the value of FD? It gets longer, and what happens to Fn? It gets smaller, right? And Fn is the value that sort of determines how much friction there is. And I think you would get that as the ramp gets steeper and steeper, there would be less and less friction, right? I'll pause it. This Fn you'll sometimes see in some books written as F perpendicular, because it's perpendicular. This is the F that's down the plane, parallel to the plane, and this is the component that is perpendicular to the plane. F perpendicular is probably a better label, but when I get into mu equals FF over Fn, this Fn is the same number as that, so I just sort of use that as a bit of a simplification. Okay? Moving on. Okay, so from the triangle, if you look at some basic sort of trigonometry, remembering that this angle here is theta. Again, this is weight force, this is Fd, this one is Fn or F perpendicular, right? If you look at this, right, we have a 90-degree triangle here. Is that always going to be 90 degrees?
Yeah.
Is the Fd down the plane going to be, yes, 90 degrees, right? So this is opposite. So this is sine. Sine of theta is Fd over Fw, which of course is equal to mg. And rearranging this, I get Fd is equal to mg sine theta. And using cos, I get Fn is equal to mg cos theta. Those are formulas. I put them in a box. Learn them, use them, love them. They're awesome. Alrighty. So here's a sample problem. I'll just give you a second or so to complete it. I just have the one. So I've got a 5 kilogram object. It's 1 meter up a ramp, and the angle is 30 degrees. And these are the things we're going to find. See that one? You maybe have even started already. Come on, next page. Right, weight force just what? M times G. Oh, wow. Yeah, it is. It's just being bad. Okay, I'm just going to have to do it all right on this page right here. I'll do a blank page. Okay, so step 1, weight force equals mass times gravity. So 5 times 9.8, and by now you should have that memorized to 49 newtons. Right? We've used 5 kilograms enough times. So 49 newtons is the weight force. The next step is to find the... Good question. Why don't we use the negative? Could we? We could. The problem arises, Mike, is if this is negative, right, then that makes that positive, right? So what is this direction then? Well, but it's not. It's kind of down and to the left, right? So in a situation like this, you could assign, if you want, you could say that down the ramp is negative and up the ramp is positive. That would be fine, right? It's just a designation to aid you in solving the problem, right? But then, well, how can this be positive? How can that be negative, right? Does the fact that this is down and negative, does the negative matter to the problem? And the answer is really no, right? Because is the object going to be going up and down? So really that negative direction never is going to actually occur. It's actually down. If anything, down the ramp should be negative and up the ramp should be positive. So that's why I purposely left it open. Is that a good enough explanation? Yeah? Good question. Okay, so I'm going to then write F perpendicular. I think that was the next thing to find, right? Is mg cos theta. So 5 times 9.8 times the cosine of 30, which is 42.4 newtons.
What's the newton again? That's like really small.
1 newton is about the weight of an apple. Yeah, that'll be enough. FD is mg sine theta, which is 49 times 9.8 times the sine of 30, 24.5, right?
49 times 9.8.
Oh, yeah, sorry, not 49 times 9.8, right? Yeah, thank you. I should have just actually copied what I had down instead of, yeah. Or 5 times 9.8, right? However you want to put it. Okay, so note that, right?
4.5.
Yeah, 24.5.
I'm on up by 2.
I don't know.
I sure 49 sine 30.
Are you in radians or degrees? Yeah, not that one. You haven't graduated yet. You can't use it. Note that the FD is the actual force accelerating it down the ramp. This handwriting thing has gotten a lot better. It is kind of neat, eh?
There's the I bet you it won't like that.
I didn't know that. FD is the actual force accelerating it down the ramp, and in fact, FD is therefore the net force in the direction that it's actually traveling. Okay, so it's the force that's going to cause the acceleration. That's the number we're going to use in F net equals ma, because that's the direction that the thing is actually accelerating. Okay? All right. So now the next thing is to find the acceleration. To find that, we're going to go F net is equal to ma. The net force is that value that we just came up with. Is it 24 or 29? 24.5. The mass was 5, giving us an acceleration down the ramp of 4.9 meters per second squared.
It's only a meter long ramp, so that's like...
It's going to get down that ramp pretty quick, you're right. Does the number 4.9 jump at you as being, no, somewhat special or unusual in some way? It's exactly half of 9.8, exactly, right. Okay, so why is that?
You'd think the angle would be 45.
You would think so, right? But,
190 maybe. Wait.
well, what's the sine and cos of 30 degrees? Go ahead. What's the sine of 30 degrees?
Sine 30 degrees.
It's 0.5. I don't think he had anything to do with it. What's the cos of 30 degrees, just for interest sake?
Well, thank you.
What is it? 0.86. Okay, so 30 degrees, yes. I had a 30 degree angle. Half of the gravity is acting down.
What is it?
Okay, so does the mass even matter here? Like, are you telling me that 30 degree angle, 0.5, 4.9, like, or is this just coincidence? We'll come back to that in a second. You don't think it's coincidence? But we're supposed to find the time to get to the bottom. Here's where we do our bridging, and we go to d equals vit plus 1/2 at squared. So that's going to be a distance of 1 meter down the ramp. 0 is our initial velocity. 1/2 the acceleration is 4.9 t squared, giving us a t value of 0.64 seconds. What's the velocity at the bottom of the ramp? That was the other thing to find. Vf equals vi plus at. Initial velocity is 0. Acceleration, 4.9. Final velocity, 4.9 times 0.64. So this thing's going about 3.14 meters per second when it gets to the bottom. So it's going to take less than a second to get there. Okay, so let's investigate that half thing a little bit more.
Is there like what does cos actually do?
In this one, the cos doesn't do anything.
Like when you like cos an angle,
Yeah.
like sine, like what do they do?
It's
is it some kind of, it's like, you know how pi is 3.14, is it something like that for cos?
Yeah, it's the ratio. If you've got an angle of 30 degrees, right? It means that the ratio of cosine, the adjacent to the hypotenuse, is always 0.86. Any angle of 30 degrees has a ratio of 1/2. The opposite side to the hypotenuse is always 1/2. This divided by this will be exactly 1/2 for every angle of 30 degrees. That's what it means. Now, on a frictionless surface, we've already agreed, right, that the FD down the plane is equivalent to the net force because there's no friction backing it up, right? So on a frictionless surface, the F net is equal to FD, which means that the net force is equal to the FD. If net force is MA and FD is mg sine theta, what happens? The mass cancels. And in fact, on a frictionless surface, acceleration is equal to g sine theta. And note that mass does not matter. It wasn't coincidence. No. The mass of an object on a frictionless surface doesn't matter. Most people think heavier things will fall faster. That is wrong. On a frictionless surface with no air resistance. There are some problems when you get some air resistance going because you have to plow the air, you have to push it out of the way, right? And there's some friction issues too. Okay. Because we all know that bigger, heavier people, if you go to Mississippi and you put 3 people on a tube, they're going to end up going down the hill faster than 1 person on a tube, right? It's a little more complicated than that. But generally, mass does not matter. Okay?
I need a picture I saw. I mean, it was like Bill Nye. He had his head down and like came out and was like, "What's the matter with you?" Yeah, he was like, "What's the matter, Bill?" And he looks up, he's like, "Everything's the matter. This is matter. That's matter." Like, yeah.
Get me that, I'll put it up on the wall. Okay, there's a few questions there in the book you could try. I also have a little handout. I think it's got 4 questions on it. I think, as far as I know, they're all frictionless. I'll give you some time to work. Next day, we'll talk more about ramps that do actually have friction on them.